Research interests include structural mechanics and computational mechanics.
The speaker that we have 50 minutes on the rules of traffic lights. Green car is always okay. Yellow car contains only 15 minutes left. Red car.
Thank you very much for the presentation. My name is Fonseca, and I'm from Polytechnic Institute of Bragança, Portugal. The title of this work is Hybrid Wood Steel Helmets under Fire. This work was made by myself and my colleagues from Polytechnic Institute also. About the topics for this work are the following. The first one is about why wood, steel, or hybrid wood steel material, the main objectives, and the thermal properties of this work. For the thermal properties, we use the rules from the Eurocode number 5 and Eurocode number 3, and the geometry is analyzed and the nodal locations for giving the temperature around the steel and the profiles. The models and fire action, the numerical simulation used, the numerical results, and some conclusions about this work. About the first topic, why wood material? The wood is a natural earliest construction material used by humanity due to the easy to use, durable, great architectural features, high strength, low weight, highly available and low cost. If I use wood material with fire action, we can have some problem or not. Wood is a combustible material, but the combustion is slower and regular when compared with other materials. When wood is exposed to agent, like a fire, for example, a shallow layer formation form insulating the section core. This is the shell layer and this is the cross section. According to the Eurocode number 5, the temperature between the shell layer and the cross section is around 300 degrees, between the shell layer and the cross section into the membrane. The wood material nowadays has a large used in the construction, like you can see in the different pictures used, for example, in build frames, pools, flowers, roofs, like these pictures in the first slide. About steel material. Why steel material? The steel material is the most common material in construction because it's extremely strong, durable, high strength. But sometimes we have many problems when the steel material is exposed to fire conditions, for example, because steel material low strength when heated, for example. Steel is a good conductor of heat. This is the most problem in this type of elements, and which produce the fire resistance of the component. And also, steel has a higher labor cost. About the applications of steel, you can see here some many applications of this type of material. And the combination between wood and steel material is our proposal. And this type of material could be a hybrid material. This combination could lead to economic and ecological benefits, weight optimization, and fire and structural resistance increase in the components, for example. And you can have an efficient assembly. As you can see in this graphic, and comparing the wood material and steel material, for example, the performance of wood members under fire conditions is higher when compared with the other type of materials, for example, unprotected steel material. And steel, as you know, melts and collapses when wood material have a shared formation and insulated the core section of the members. Here we can see some different applications using, for example, wood steel material. As you can see, we can have a new building projects, for example, like the first two pictures, and bridge and slabs also. Okay, and now the main objectives of this work are the following, and the first one is produce the temperature time history for different 24 design models submitted to different fire conditions. Another objective is to verify the best constructive model to increase the fire resistance of the member. All models were developed using the fine element method, and the simulation is a thermal simulation using a transient analysis with HANSES program also. And for this, we use the plain fine element, like this one, with 8 nodes by elements and 1 degree of freedom by node for temperature nodal situation. Also, in whole study model and for transient thermal analysis, we need to use the standard time cube, like this picture. You can see the proposal according to Eurocode number 1. About the thermal properties used in our numerical models. The thermal properties are used for wood and steel. You can see here in the first picture the thermal properties for wood, and the second picture gives us the thermal properties for steel, both according to Eurocode number 5 and Eurocode number 1. And also these properties are temperature dependent of the properties. As you can see, there is a peak in this value for the wood material because this is the temperature where there exists a water evaporation process. And the same for steel, there is a peak for the specific heat due to allotropic process during the process. About our modeling, we use 3 different models, like the first one, the second, and 3. And the geometry are different, but the length and the weight of the models are similar. And all models are submitted to different fire conditions. For the first one, you can see 1 front of fire condition, and the second models we can see 3 front of fire exporter. In whole models, we use 4 nodal positions at the same length and to measure the temperature during 1 hour of fire exporter. The combination between the 2 materials, wood, steel, and the combination between wood and steel material give us 24 different models, as you can see in this picture, to obtain different temperature around the same nodal positions. 4 of this model, as you can see here, there are internal cavity. We use 2 different combinations where we can model the air internal this cavity and this one, and give similar results when we don't have internal air of the cavity. For numerical simulation, all temperatures were obtained during 1 hour of fire exposure, and the boundary conditions in whole models are convection and radiation according to the temperature evolution in fire, and also an initial temperature equal to 20 degrees in whole models was considered. The evolution of fire was defined by the standard curve, like this equation, and for model number 3, we modeled the air internal, and we use okay, I'm so sorry. And we use these graphics for specific heat, density, and thermal quality for the neck. Depends on the temperature. According to the numerical results in form model number 1, we can see in this slide the model number 1 with 1 fire of exposure in one side, and here we can see the results for the same model, but consider 3 sides of exposure fire. We have the post-processing for the 1 hour of fire exposure, and also the time history for all 4 nodal positions in all models. In this slide, we can conclude that the elements that have wood in front of fire exposure, like this one, the first line and the last line, protects the core section. The core section is always at lower temperature, and still in front of fire quickly hits all process, like the third and the fourth line of this component. Numerical results for the model number 2, also for 1 front of fire and 3 sides of fire. We have the similar conclusions, but now with a different general conclusion, because the model number 2, the steel has better performance when compared with the wood materials. Why? Because the wood elements in front of fire are very thin in this model and quickly lose their resistance due to the shard layer formation in front of the fire situation. And for the last model, we can see the same results at 1 hour of fire exposure. In the first column, we can see the models when we have 1 front of fire, and here 3 front of fire exposures. The main conclusion about these results is when wood is externally applied to steel, plays an important role as an insulation, because it protects the inside of the component, and the inside of the component is always in steel in this model. In case where both outside and inside of the model is steel, the temperature in the inner profile is higher and is not important when compared with wood and steel material. The general conclusions are similar, and according to the results, wood elements present lower temperature than steel, and the maximum temperature in the model is always inside the shard layer in the wood members, and the fire exposure at 3 sides is the worst fire situation, always, and the hybrid models can perform well under fire conditions in whole models, if the model air gives similar results to the internal insulated elements. Only shows the heat conduction inside the element. And the best design solution in the 24 study models is the hybrid model number 3 with the 3 fire side exposure to fire and hood outside and steel inside. This model has a good fire resistance even for 3 side exposure, showing the ability to wood and to protect the steel internally. And thank you very much. This is a little picture about the bidimensional problem and the 3-dimensional problem.
Thank you. Are there any questions for the speaker?
A felicitarle por el buen trabajo que ha hecho. Ha transformado mis trabajos prácticos de laboratorio en estos modelos computacionales. Enhorabuena.
Gracias.
Any other questions? Linda.
Grandiose Technical University of Denmark. What is the importance, given that you have time temperature curve, which is typically done in a furnace. What is important? I don't quite understand how you apply it from 3 sides, given that it's a time temperature, so it would be a uniform temperature field that is put into.
Okay. This is a thermal transient analysis using finite element methods, and I use the solid program with ANSYS interactivities. And we use the ISO-Q to simulate the temperature environment when there exists a fire situation. This is a role according to Eurocode number 1, and I choose the ISO-Q for this situation. And for that, I use the boundary conditions like convection and radiation, and the temperature environment increase according to this type of Q in our simulations. And I use this simulation for one side, for example, and the 2 other walls are insulated, for example, or when I have three walls with 5 actions and without insulated walls, for example.
Looks like we have time for one more question. Okay. I was wondering, you talked a little bit about the evaporation of moisture. Was your work done for one particular moisture content? And would you expect there to be any variation for, say, a dry climate versus a humid climate where the wood would have more moisture?
Okay. According to moisture, I use only the thermal properties from the Eurocode number 5. The specific heat as a peak at degrees Celsius, and is the water evaporation, okay, in the chamber solutions. Okay, this is only a numerical simulation. Okay, we don't have an experimental tests here. If I have experimental tests, I need to control the moisture, and I need to verify if it is according to the Eurocode around 12% of water evaporation in this peak.
Okay, thank you. Let's thank the speaker one last time.